Here are solutions to homework set number 5 for ECE 463-663 Modern Control. This homework set looks at full state feedback, or Gura. The first problem is write a MATLAB function where I pass the dynamics of the plant, A and B, the desired feedback gain, or desired pole locations, P, and return the feedback gains Kx so that the roots of A minus BKx are my desired pole location. So this uses an algorithm called Gura. The similarity transform to go from any form to controller canonical form is T1 times T2 times T3. T1 is the controllability matrix, so that's your B, AB, A squared B, and so on. That's T1. T2 is a function of the polynomial, characteristic polynomial of the system. So here's the characteristic polynomial, and start shifting it to the right. T3 is the elliptic matrix, one's on the up diagonal, so T is just T1, T2, T3. The way Gura works is in controller canonical form, the feedback gain is just the difference in the characteristic polynomials. So that's the feedback gain in controller canonical form. The feedback gains in your state variable form is similarity transform kz times the inverse of t. As a check, if I have A be a random 4x4 matrix, B is a random 4x1 matrix, put the closed loop poles at minus 1, 2, 3, 4. Here's Kx, and as a check, write the poles where I put them, and sure enough they are. So it looks like it works, at least in this case. Now problem 2, and thereon, says let's look at a fifth order system. This corresponds to a 5-stage RC filter where 1 over RC is 5. That gives you these dynamics, if you care. Problem 2 says find the feedback gains to put the closed loop poles at minus 1, 2, 3, 4, 5. What that means is I want the step response to look kind of like this. The settling time is roughly 4 seconds, ballpark. A little bit longer because these poles aren't that fast relative to minus 1. So minus 4 or 4 seconds-ish with settling time, no overshoot. If that's my desired response, that's where I want to put the poles. How do you do that? Well, input the A matrix and B matrix. Use our handy pole placement algorithm to put the poles at minus 1, 2, 3, 4. I get 5 feedback gains. If you check, the eigenvalues of A minus BKx are sure enough at minus 1, 2, 3, 4, 5. Pick Kr to make the DC gain 1. So here's the DC gain without Kr. DC gain is 26. Pick Kr to make the DC gain 1. There's Kr. Here's Kx. The closed loop system is then, here's the closed loop A matrix, closed loop B matrix. C and D don't change. Take the step response, and here's what you get. So there's the step response to Y. I also plotted the input. This wasn't required in the homework, but it's kind of fun to see what's happening. Change the C and D matrix. If C is minus Kx, D is Kr, that produces U, the input. So plot the step response to Y in blue, step response to U in red. There's your step response. You kind of what you expect. No overshoot, I've got real poles, settling time is 4 seconds-ish, and there's the input that it takes to get there. Problem 3 says I put the poles at kind of an arbitrary spot. The pole at minus 1 makes sense. That specifies the settling time. Suppose I just care about the dominant poles. The other 4 really don't matter. They're not dominant. One thought is wherever the open loop system's poles are, leave them alone. It should take no energy to do nothing. So if I do that, put the dominant pole at minus 1, put the other poles wherever they were. What happens is the feedback gains become much, much smaller. I still have the same settling time, same dominant pole, but the feedback gains went, you can find it, from, biggest poles at minus is 30, 31. Now the gains are, less than 0.4, less than 0.5. Another thing I like about these gains, I don't like the negative sign. I'm using negative feedback. A negative feedback is positive feedback. Positive feedback tends to make things go unstable, so I don't really like these negative gains. By putting the poles where the open loop system poles are, all the gains are positive. That's good. They're small. That's good. Probably a better set of gains. Throw in KR to make the DC gain 1, and you get a number. Now take the step response to the closed loop system. Again, here's the closed loop A, closed loop B matrix. Change C and D. This gives me U. So here's the step response to Y. Here's the step response to the corresponding U. Again, the output looks almost exactly the same. Same dominant pole, basically the same system. The input is maybe better behaved. Where it really shows up is the gains are all positive and small. Problem 4 says, can I make it oscillate? So here I want the step response that looks like this. I want to have a 2-second settling time, 10% overshoot. So there's the step response I want. Come up with the feedback control law that does that. Well, what I did is I just specified the dominant pole. The real part should be -2 for the 2-second settling time. The damping ratio should be 0.59 for 10% overshoot. Putting that together, take the arc cosine, tangent. Here's the complex part. You're basically in the S-plane. The real part's at -2. I know the angle. That tells me the damping ratio. Given the real part and the angle, I can tell you the complex part. That's J 2.72. Here's where I want the dominant pole. Well, this tells me where 2 poles go, the dominant pole and its complex conjugate. I've got 5 poles, however. So where do you put the other 3 poles? I'm going to put them wherever they are in the open loop system. Again, kind of arbitrary, but that's kind of one approach. The poles that are fast, leave them alone, but move these 2 poles right here. So doing that, here's where I want to put the closed loop poles. Find the feedback gains using pole placement, and I get 4 numbers. Again, what I like about these numbers is they're fairly small. They're all positive. I like that. This one's getting kind of big at number 3. What's happening is heat equation, RC filters don't like to oscillate. If you push them, I can do anything I want, but it takes energy. That's why these gains are getting kind of big. I get a corresponding KR. Now plot the closed loop step response from the closed loop system to Y, closed loop system to U. Plot the step response, and here's what you get. So this is Y. This is actually U over 10. I divided by 10, essentially divide by 10, just because it was going off the scale. And what you're seeing is to get the thing to oscillate, I really need to slam the input, get it to go above, go negative, go below steady state value, and then let it settle out. So I can make it oscillate. And heat equations don't like to oscillate, but if I have enough input, I can do it. So that is homework set number 5 for ECE 463 Modern Control, pole placement. The beauty of pole placement is you can put the poles anywhere you want. The weakness of pole placement is the dominant pole. You kind of know where that one belongs. That tells you the step response. All the other poles, it's really unclear where you should put them. But on paper, it doesn't matter. In practice, some places work better than others. What kind of worked here is if the open loop system is already fast, leave the poles alone. But that's homework set number 5 for 463.